Good morning. My name is Junzi, and I am a fifth-year graduate student at Stanford. Today, I'll be talking about the lubrication mechanisms of the ocular surface. I want to mention that this is a collaborative project between Novartis and us. Our ocular surface is important yet fragile. Normally, we have a lubricious, low-adhesive ocular surface, which can ensure healthy blink cycles. It is impressive to think how ocular surface is maintaining its lubricious nature. On average, we blink 10 to 20 times per minute, which amounts to millions of blinks per year. For most synthetic soft materials, it is hard to avoid deterioration and wear on the surface over this many loading cycles. However, nature figures out a lubrication mechanism that ensures low friction over long periods of time. But there are cases when this mechanism fails, and that will lead to dry eye disease, in which the patients experience pain, discomfort, or blurred vision when their eyes are open. Dry eye disease remains the top one reason that patients visit ophthalmology practitioners and has huge societal costs that affects hundreds of millions of people around the world. But its pathology still remains elusive due to a lack of understanding in the lubrication mechanism at the ocular surface. In this talk, we hope to provide some thoughts and hypotheses on this fundamental question. Human ocular surface is generally considered to consist of a corneal epithelium and a tear film. The human corneal epithelium has 6 to 9 layers of stratified corneal epithelial cells that express three major membrane-tethered mucins. Mucins are a large family of glycoproteins that are expressed mostly by epithelial cells, and its richly glycosylated and negatively charged central domains hydrate cell surfaces and lubricate cell motions. On top of corneal epithelium, we have a thin layer of tear film that stabilizes the ocular surface. This liquid film hydrates the corneal epithelial surface, protects it from external viral and bacterial infections, and also lubricates the interface between corneal and conjunctival surface during blink cycles. And conjunctival epithelium is the epithelium that's lining the surface of our inner eyelid. One reason that we don't yet have a clear understanding of the lubrication mechanism at the corneal surface is that we lack a controllable as well as physiologically relevant model. In the past, friction at the biological surface has been modeled by protein absorbed on mica surfaces, mostly as SFA or AFM studies. While the chemistry of this surface is controllable, there are two important distinctions between this model and actual biological surfaces. First, it is hard to recapitulate the topology and morphology of cell surface in a synthetic model. And second, the viscoelasticity of the cell layer is omitted from this model. On the other extreme of the model ocular surfaces, we have small animal models which does recapitulate the complex nature of native ocular environment, but these models are usually hard to quantify and control. So in this research, we developed a cell culture-based dry mimetic ocular surface model, or DEMOS for short, which we hope will bridge the gap between synthetic and animal models. And with demos in this presentation, I will show that both surface roughness and surface chemistry contribute to the lubrication mechanisms of the ocular surface, similar to that of a liquid-infused surface. The cell model that we use to represent the ocular surface are differentiated corneal and conjunctival epithelial cell lines. Under low calcium conditions, these cells grow into a monolayer with minimal cell-cell junctions, and the epithelial cell layer takes a cobblestone morphology. However, when cultured in high calcium conditions, the cell will start to differentiate towards a squamous-like morphology over the course of several days. To test if this differentiated corneal cell surface can recapitulate native ocular surface, we did some immunofluorescence staining on MUC1, which is a major membrane-tethered mucin. Here we see that differentiated corneal and conjunctival epithelial cells express substantially more MUC1, which is showing green channel here, after 7 days of stratification or differentiation process. In addition, the localization of ZO1, which is a tight junction marker for mature epithelium, shifted from the nucleus to cell-cell junction near the apical surface after 7 days of stratification, similar to the molecular features of native human ocular epithelium. To mimic the altered mucin expression observed in many dry disease patients, we utilize a recombinant protease extracted from E. coli, which is called sticky. Sticky targets a peptide consensus sequence commonly found in mucin and mucin-like glycoproteins. We use sticky-treated differentiated corneal and conjunctival epithelial cell layers as our mucin-deficient drymomatic ocular surface, or demos. In our study, we verified the sticky activity by both immunofluorescence scanning against MUC1 and a lectin staining against O-glycans. Here you can see that an overnight incubation with 5 microgram per ml sticky has substantially depleted the MUC1-rich layer on the cell surface on this lower left panel. On the right, we have done a sticky treatment from low to high concentrations for a fixed amount of time. From the reduced signal in both red and green channel, we see that there is a dose-dependent decrease in cell surface glycoproteins with increasing sticky concentrations. Overall, we think demos recapitulated the mucin-deficient ocular surface observed in some dry disease patients. To study the interfacial properties of demos and how this property is linked to the lubrication mechanisms of the native ocular surface, we measure the contact angle hysteresis and the stress relaxation response at cell-cell interface. To study the to measure the contact angle and contact angle hysteresis of live cell surfaces, we utilize a captive bubble method in which the cell surface are immersed in PBS facing down in a liquid chamber. Then a capillary needle generates an air bubble around 5 microliter that will freely attach to the cell surface. Then we can use image analysis to extract contact angle as cell, air, and liquid triple line. The stage can then tilt with a defined speed, and we can calculate the contact angle hysteresis, which is defined as the difference in the cosine and of the advancing and receding contact angle when the air bubble escaped from the cell surface. Since mucin molecules are generally considered to be responsible for the hydrophilicity at the cell surface due to their negative charges enriched hydroxyl groups, we first hypothesized that after sticky treatment, the cell surface will become less hydrophilic, and therefore we should see a drop in contact angle. And notice that since we're measuring contact angle in a captive bubble geometry, lower contact angle corresponds to higher hydrophobicity. However, from the results, we saw that the contact angle were consistently around 156 degrees for all conditions that we tested, which includes monolayers before and after sticky treatment and differentiated layers before and after sticky treatment. There's no significant difference among the two groups. What this tells us is that first, this high value of contact angle indicates a superhydrophilic surface, which is required to maintain a stable tear film in our eyes. And then the indifference to sticky treatment tells us that mucin is not the only contributor to the hydrophilic nature of the cell surface. Glycoproteins other than mucin on the cell surface are sufficient to maintain the hydrophilic nature. In contact angle hysteresis measurements, we saw an increase in hysteresis after the differentiation process, similar to what other groups have observed in previous experiments. This leads us to ask why we're seeing this increase in the hysteresis after differentiation process. Previously, Yanez Soto and co-workers hypothesized that the heterogeneity of mucin expression on the epithelial surface might have contributed to this increase. If this hypothesis is correct, then we should see a drop in hysteresis after sticky treatment, as sticky treatment should homogenize the cell surface by clipping off all mucin molecules on the cell surface. But similar to contact angle measurements, sticky treatment did not significantly alter the hysteresis value, which means mucin is not the major contributing factor here. This leads us to think about other potential factors. Since advancing and receding contact angle can be caused by either a chemical defect, like the heterogeneous mucin expression as we have been talking about, or a physical defect, such as a superhydrophobic point defect, we then went on to test if surface roughness can induce a change in the hysteresis value. To induce changes in surface roughness, we added a calcium chelator EGTA into the medium. As cell-cell junctions are dependent on calcium divalent ion, EGTA will cause the cell-cell junctions to dissociate and change the overall morphology of the cell surface. To quantify the cell surface, we scanned the lipid bilayers of the epithelial cells and reconstructed the cell surface from fluorescent confocal images, which are shown here as heat maps. We define the cell surface roughness as the root mean square of height deviation from the mean height value. What we found was that for large fields of view on the order of 400 microns, the squamous-like differentiated cell layers actually exhibit larger roughness compared to monolayers, and EGTA treatment increased this roughness even further by releasing the tension at cell-cell junctions as expected. We then go back to compare the data of roughness and hysteresis. We found a nice correlation between these two quantities. And the right boxes here are highlighting the data that can be compared with the roughness on the right. So after looking at this, we think roughness does contribute to the hysteresis value. And physiologically, a high hysteresis value means that the cell surface has more retentive force on the tear film, which is desired for better lubrication. Next, we're wondering if mucin contribute to the dynamics of blink cycles. During a blink cycle, we have the surface of inner eyelid sliding over the surface of cornea, and we mimic this geometry in a customized live cell rheopter, or LCR for short. In essence, LCR is a sliding plate rheopter mounted onto a microscope. To prepare the sample, we culture corneal epithelial cells on the bottom plate and conjunctival epithelial cells on the top plate. Before the experiment, we load the top plate onto the bottom plate, wait for 2 hours for the adhesion to form, and then perform a step strain experiments by monitoring the stress value reported from a force sensor. Here on the right, I'm showing a representative graph where you can see the peak modulus quickly relax to a stable long-time plateau modulus, reminiscent of a viscoelastic solid rheological behavior. In the first set of experiments, we tested whether the lack of mucin can alter the adhesive strength at the corneal conjunctival cell interface. Here I'm showing the average stress relaxation graphs for this cell-on-cell model. Here the orange curve is the control case, while the blue curve is the sticky treated case. The shaded area around the relaxation curve is the standard error from multiple experiments. We see that there is a slight increase in the apparent modulus after sticky treatment. Here we quantify the residual modulus, which is defined as the long-time plateau modulus. To calculate this value, we fit the relaxation curve to a double exponential decay function, which is shown as the black dashed line here. After quantification, we saw that the plateau modulus increased by 70% after the sticky treatment, suggesting that our demo's model indeed exhibits a stronger adhesion at cell-cell interface. To confirm that this effect is indeed induced by interfacial phenomena instead of a change in the bulk cell mechanics, we went ahead and did AFM single-cell mechanics and found that sticky treatment does not alter the Young's modulus of the single cells after sticky treatment, confirming that the increase in the plateau modulus indeed comes from a stronger adhesion at the interface. To further test the notion that mucin-like glycoproteins can reduce cell-cell interfacial adhesion, we added a mucin-like glycoprotein lubricin into the sticky treated demo model. Lubricin is a glycoprotein that was first found in the synovial fluids between our articular cartilage in the knee. It was then found by a small amount in our eyes as well. Lubricin has been hypothesized to lubricate many biological surfaces. Here we're using a recombinant version of the human lubricin as our potential mucin-like glycoprotein candidate. We first tested the absorption of recombinant lubricin onto the live cell surface through fluorescent microscopy. Here you can see that on controlled corneal epithelial cell surface, we have a substantial amount of signal from fluorescently tagged lubricin, which is expected as lubricin tends to associate with cell surface glycoproteins. After sticky treatment, the absorption of lubricin has been substantially reduced, but still higher than our negative controls. The absorption pattern also appears more clustered, as we hypothesized that lubricin molecules aggregate around the residual mucin molecules left on the cell surface and form these clusters. After adding recombinant lubricin into the surrounding medium, we saw a reduction in the apparent modulus. Here, the blue curve is without lubricin, and the orange curve is supplemented with lubricin. We have tested the effect at different concentrations of lubricant, and it seems that there is a gradual decrease in the plateau modulus as we go higher in concentration, and the effect is saturated around 300 microgram per ml. So coming back to our initial question as to what is the lubrication mechanism of the ocular surface. I hope I have shown through the two essays here that both surface roughness and surface chemistry, especially the presence of mucin-like macromolecules, contribute to the interfacial property of the model ocular surface, which is reminiscent of the liquid-infused surface in which the oil-based lubricants are perfused onto textured substrates. Their both controlled texture and choice of oil lubricants are paramount to the final lubrication performance. With that, I will conclude my talk. I would like to acknowledge my advisor, Jerry, for giving me tremendous amount of support, and Dr. Amy Meadow, who I have collaborated with extensively on this project, and soon to be Dr. Kayvon Pandren, who has provided us with sticky enzymes and just so many inspirations on the projects. With that, I'm happy to take any questions.